So today we're going to finish up this class in continuing our discussion on controls. So today we're going to focus more on some specific controls strategies that we can use to save energy with our HVAC systems. The first strategy is what's called morning warm-up. So we talked about last time about occupied and unoccupied space temperature set points and how, say, on nights and weekends in the winter, will allow our buildings to cool down, or in the summer, will allow them to warm up when nobody's in there. But let's say we have this scenario where we're setting back our building to 55 degrees at night or on weekends in those winter months, but we need that building to be comfortable when people show up the next day at 7 in the morning. And it's not like we can just instantaneously get our building from 55 degrees up to a comfortable 70 degrees. That's not a switch that you can just flip and make happen. So how do we get the building comfortable before people show up? The easiest way to do it is you just take that occupied start time and you just set it earlier. You know people aren't going to be there until 7 o'clock, but let's just say, well, I'll set my occupied start time at 5 o'clock every morning. That gives the building 2 hours to warm up and get up to temperature. And this is something that we see very commonly, but there are some issues with using that as your morning warm up method. Problem one, if we are setting our system to be in occupied mode, that typically means we are bringing in ventilation air. That is an inherent part of what occupied mode means. We're bringing in ventilation air. And we know tempering that outside air takes a lot of energy and takes a lot of money. We also probably don't need to start our systems at 5 o'clock every morning. If we had a mildly cold night, or if we're in the shoulder seasons where we're kind of in between heating and cooling, we probably don't need to start at 5 o'clock every single morning. And so you're likely going to end up with some excessive run times if you start at 5 o'clock every day. A better way to do this is with a proper morning warm-up mode, which does two important things. Number one, it closes the ventilation during that morning warm-up period. So we are turning on our heating equipment, but we are leaving the ventilation dampers closed and going into a 100% air recirculation mode. So this is going to lead to reduced heating energy because we're not having to heat our ventilation air during those morning warm-up hours. Another benefit here is if you take out that ventilation load, that leaves you with heating capacity that you can use to instead warm up the building. So you'll be able to warm up the building faster because now you're not having to use any of your heat capacity on the ventilation. You can use it for your building heat. The second thing that a morning warm-up sequence is going to do is what's called optimal start. And what this means is your control system looks at the weather to figure out the right time to start equipment, to bring it up to that occupied set point in time. And it's important that we're saying you have to look at the weather to determine that time. So on some mornings, you might only have to start at 6:30 to get up to temperature by 7 o'clock. But then on a colder morning, you might have to start at 6 or 5:30 or even 5 o'clock. And the specific method for how to do this can vary a little bit, but the intent is the same. You have to have some kind of programming in place that will dynamically change the start time to bring your building up to temperature at that occupied start time. And most energy codes nowadays require some kind of optimal start programming, in addition to closing the ventilation dampers during morning warm-up, because that morning warm-up period is still unoccupied, so we shouldn't be bringing in ventilation. So the basis of savings with the optimal start is we can reduce our fan energy and our heating energy by optimizing when we actually turn on that equipment. To help visualize this, so let's say we're going to look at our space or building temperature over a period of time. Let's say the red line being our set point where we want to be. So before we go into our unoccupied setback, our set point is 70 degrees and our actual space temperature is maintained around that point. You still have some oscillation there, but it's around 70 degrees. And then our building goes into unoccupied mode. And that's effectively an instantaneous change. So that part is like a switch. We go straight from 70-degree set points down to 55 degrees. But that doesn't mean our building instantaneously drops down to 55. You're going to have this gradual decrease in our actual space temperature as the building cools down. And then it's going to hit that 55-degree set point. And now we're in that unoccupied heating mode where the system is cycling on and off to maintain just 55 degrees. Then we get to the morning and we have another instantaneous point where, well, at 7 a.m., we want the building at 70 degrees, but we can't just make the building increase in temperature by 15 degrees. That part's not a switch. So we have that morning warm-up period where we have to figure out some start time, right around here, where we need to kick on the systems in order to reach that point by that occupied start time. And then from there, we're back into occupied mode until this starts over the next night, or might go into the weekend to do the same thing. But that's what that morning warm-up would look like in actual practice. Morning warm-up is clearly, well, it is the most beneficial in those heating months. Not as beneficial in the cooling months, but we can apply it in those cooling mode days as well. So that would be morning cool down as opposed to morning warm up. So if we're in the summer, we have a long weekend, we could set our building back to 85 degrees. So we're raising the temperature of the building, and then now we need to cool it down before occupancy starts. But we do the same thing. We only start the equipment when we need to, and we don't provide that ventilation air. One exception, though, to that ventilation air piece is we might be able to utilize economizer. If we can get free cooling on a cool morning, then that's a great way to cool down our building without using a lot of energy. And even in those summer months, those mornings are still kind of cool. Even in the peak of summer, outside it might be 60 degrees early in the morning, and we can use that to help cool down our building instead of running our chillers or our air conditioners or whatever we have for our primary cooling equipment. Second strategy is what's called staggered start. If you think all the way back to when we talked about utilities typically charge for the peak demand, which that peak demand is the largest instantaneous electric demand that was seen during that month. Doesn't matter how long of a period that demand was seen. If the utility looks at your building and they see, well, on this day and at this time, you pulled 300 kilowatts from the grid, we're going to charge you for that peak demand, even if it was just for a 15-minute period. Now let's say we set our building back to 55 degrees. So everything's kind of coasting. But then as soon as that morning warm up cycle is enabled, then we have this moment where everything kicks on at the exact same time. And often it kicks on at full capacity because we're trying to recover from that setback period. And so everything has to work much harder to get up to that comfortable temperature by the time people show up. So that is very likely going to set your peak demand for the month because everything is kicking on at the exact same time. And now you've just set your peak demand. This is especially bad if you have electric resistance heat. If you're heating with gas heat, gas doesn't have a demand charge associated with it. So you would only see the demand associated with the fans. But if you have electric heat, that is a lot of kilowatts, and that is surely going to set your demand. So a better option here is we do a staggered start of our equipment. So during that morning warm-up period, we write into our control logic, we say, I'm only going to allow, say, 5 units to be running at any given time. So we start 5 units, and then one of those units will get up to temperature, then that one will turn off, and then the next in line will turn on. And you do that across your entire building to prevent everything from turning on at the same time. Now, what this means is you might have to start some of your equipment earlier because you're slowing down the overall heating up of your building. Now we might have to start things at 5 a.m. instead of 6 a.m. in order to still get the building up to temperature on time. And because of that, you might end up increasing your energy use because we started some equipment earlier than we would otherwise. And so our overall kilowatt hours or therm use may go up, but the hope is that we can reduce our demand charges to make up the difference. So that would be the basis of savings. If we can stagger the start of our equipment, we can reduce our demand charges. We still might incur more energy use and cost, but hopefully it will skew on the positive side and have overall positive savings. Next strategy is demand control ventilation, which is often abbreviated as DCV. I'll say it again. Ventilation air is expensive, a lot of energy. And when we design our systems, we have to design them to provide ventilation for the design occupancy, which, thinking back to how a design engineer thinks about things, what's the worst case scenario? What's the most number of people I can expect in this classroom or in this conference room or in this big open office? And then I have to design my system to be able to provide that much ventilation. And the old school way to do it is you just provide design ventilation all the time. We would end up over ventilating the spaces most of the time, which isn't necessarily a bad thing, but that does take a lot of energy to do. So that's the old school way to do it. But how often is the worst case condition? A lot of times, not that often. And that brings us to this solution of doing demand control ventilation, which the idea is we're only going to provide just enough to maintain what is considered adequate indoor air quality. As an example, if you have a classroom designed for peak 30 students, but maybe the actual occupancy is only 20, or you might have several hours of a day where that classroom is completely empty. Maybe that class goes to they go into the gym for a bit, or they go into the library or computer lab, and there are several hours each day where that classroom is just completely empty. So then we need to figure out, how do we vary our ventilation? If we're saying we're only going to provide just enough for how many people are actually there, well, how do we do that? We don't have a people counter. You can't install a device in a classroom that counts the number of people in a space. At least they haven't invented that yet. So what we do instead, we provide enough ventilation air to maintain adequate CO2 levels in the space. And we measure that in parts per million, or ppm. If more people go into the room, that increases the CO2 level in the space, and then that tells the control system we need to put in more ventilation air because we're seeing an increase in CO2. And if we see less people, that's a decrease in the space CO2, and that tells the system we can cut back on our ventilation air. And this generally has pretty good payback. It's kind of similar in concept to occupancy sensors back when we were talking about lighting. If you install that occupancy sensor on a lighting system, that's a very good way to dynamically control the run hours of that lighting system to only turn the lights on when people are actually there. Same idea here, only provide ventilation when people are there, and dynamically adjust the ventilation based on how many people are there versus not. In new construction, the energy code nowadays generally requires this to be done, with some exceptions. And it's also possible to do demand control ventilation based on some other fumes that aren't carbon dioxide. So when we talked about the Spokane Transit Authority maintenance garage, I briefly talked about this, where we installed carbon monoxide and nitrogen dioxide sensors in the space that would increase and decrease the ventilation air based on those fumes, because those are the fumes that vehicles emit. So it's not always about CO2, although it usually is, or at least that's the most common application. One of those sensors in a space would look something like this. A lot of times they are integrated into the thermostat. So you can see this actually shows what the temperature in the space is as well. If I was teaching this in the classroom, I would walk over next to the light switches, next to the thermostat. In Gonzaga's classrooms, or at least the ones I've been in, they all have one of these sensors right on the wall. And sometimes if you look at the sensor when you first walk into the classroom, you can look at the reading. And then after you have an hour where everybody's in that classroom and generating CO2, you can look at the sensor again when you leave and see that it's actually reading a higher value. To try to visualize this a little more, so let's say this is our classic ventilation design, where we provide a constant ventilation for that design occupancy. We might have a variable occupancy throughout the day. So in this case, we had 2 events during the day where we had very high occupancy. And let's say we are just providing a constant ventilation airflow. It's designed for worst case. What would happen with the CO2 level is the CO2 level in the space would rise and fall with the occupancy. So as people enter the room, you would see an increase in CO2 and vice versa. So they would essentially follow parallel with each other. And let's say our what we consider a safe CO2 level is 900 parts per million. We can see that our CO2 level in the space, it's only approaching that maximum limit when the room is fully occupied. So every other hour of the day, our CO2 levels are really low, well below this safe level. And what that means is we are over ventilating most of the time. Compare this to a demand control ventilation design. Let's assume identical occupancy, the same exact room. So we have two events where we see a large increase in how many people are in there. But now we're going to vary the ventilation with our occupancy. So as people load up, our ventilation is going to increase and vice versa. We can use the same safe CO2 level of 900 parts per million, and our ventilation is varying to meet that CO2 level set point, meaning our actual CO2 levels are going to oscillate right around that 900 parts per million. And quick side note, if I set this at 900, just like a temperature set point, we will get some oscillation here. If I truly wanted 900 as my maximum upper limit, I'd have to set my set point a little bit lower, say 875 parts per million, because it's always going to go a little bit above and a little bit below, and it'll hover around whatever you set it at. But the idea, we're only providing what's needed to maintain that 900 parts per million, because that is what is deemed an acceptable indoor air quality. And the savings, if we compare a constant ventilation here as our flat line as compared to our variable ventilation, you can see they still hit the same peaks when the room's fully occupied, but this hatching shows how much savings you could see. Next up, we have what are called temperature reset strategies. Think back to when we were talking about chillers, boilers, air handlers. Multiple times we've talked about the efficiency benefits that can result from changing our temperature set points. To refresh your memory with some examples, let's say we have a hot water temperature set point. Our typical design hot water supply set points are 180 degrees in a non-condensing boiler or 140 in a condensing boiler. If we can reduce those set points, we can have less distribution losses in our piping, because now we're running cooler water through our building, meaning there will be less of a temperature difference between the pipes and the building. So that's reduced distribution losses. And if we have a condensing boiler, this one is the bigger deal. If we have a condensing boiler, if we can turn down our hot water supply, that will also have a corresponding reduction on our hot water return, which makes our condensing boiler more efficient. Because remember, condensing boiler efficiency is completely driven by that return temperature going into the boiler. So it's advantageous to reduce those set points and increase the efficiency of our boiler if it's a condensing boiler. Or if we had a chiller, we can change the chilled water temperature set point. Typical design set points are right around 45 degrees. That's what we send out into our chilled water system to all of our chilled water coils. But if we can raise that temperature up and produce a little bit warmer water, we can gain 1 to 1.5% efficiency for each degree that we raise that water, which comes back to this idea of chiller lift and how much work does that compressor have to do. So if we raise our set point, we are raising our evaporator refrigerant temperature, which reduces kW per ton. So again, there are efficiency gains there if we can raise that chilled water set point. Or what if we wanted to change our supply air temperature set point? If you have a VAV system, recall that's one of the systems that is always providing cool air. usually around 55 to 65 degrees all the time. And then you have the reheat boxes that will heat up the air before it gets delivered to each individual space. If we can raise that temperature up, that supply temperature leaving the air handling unit, well, now that's less cooling energy and potentially less reheat energy at the reheat coils. The idea is we're kind of preheating the air a little bit more at the air handling unit, and now the reheat coils don't have to work as hard. So there are benefits here, but we can't just go in and just change these set points. If we reduce the hot water set point, we reduce our heating capacity. Same thing on the chilled water side and the supply air side. If we increase those set points, we reduce our cooling capacity. So we need a smarter way to attack this problem, to change our set points when we can, or when it's appropriate to do so. So we still need to maintain those design set points when we have those peak load conditions, and only change them as the load decreases. And anytime we're changing these set points based on some strategy, some programming or logic, that's called a temperature reset strategy. Easiest way to do this is based on outside air temperature. As you've been doing our bin calculations, we've been using outside air to predict our heating and our cooling load. If we have a high outside air temp, that means high cooling load, or low outside air temp is a high heating load. And so we can use that to potentially change our set points. If we have a hot water system, let's say if we are at or below 20 degrees Fahrenheit outside air temperature, I'm going to set my hot water supply to 180 degrees, which would be my design temperature, worst case condition. So if I'm really cold outside, I need hot water. And then if I'm at or below, or excuse me, at or above 60 degrees outside air temp, I set my hot water supply to 140 degrees, which would be my low heating load condition. So it's pretty warm outside at 60 degrees, or moderately cold, however you want to think about it. And so we don't need as warm of water to heat our building. So those are the limits. And then if we're in between 20 and 60 degrees outside air temperature, we interpolate between the two. So if we are at 40 degrees Fahrenheit, we will be at 160. And if we're at 35, we'll be somewhere else. If we had a chiller, we could do something very similar. If we're at or above 90 degrees, so hot day, set our chilled water supply to design 45 degrees because we need that cooling capacity. But if we're at or below 60 degrees, we don't need as much cooling, so raise our chilled water supply to 55 degrees. And then in between, we'll interpolate our set point between those two limits. To put it visually, here's what it would look like for a hot water system. So our hot water supply is at 140 degrees. If we are at or above 60 degrees outside air temperature, we'll be at 180 degrees if we are below 20 degrees outside air temperature. And then in between those values, we'll interpolate. And a chilled water system would be very similar, essentially just inverted. And we can use similar logic if we're trying to reset supply air temperature. So if we are, again, at a hot day, set our supply air temperature to a cold 55 degrees because we need all that cooling. If we're at or below 60 degrees outside air temperature, we don't need as much cooling, increase supply air temperature. and interpolate in between those. So these are called outside air temperature based reset strategies. And these have been used for decades. They're still used today. The energy code still says this is an acceptable way to reset your hot water or chilled water or supply air temperature. The advantages of this is very easy to program, and it's easy to understand, and it's easy to adjust. If you find that, well, when I'm sitting at a 40-degree day, my hot water is just not quite hot enough. You can easily go in and change the limits of that algorithm. And maybe instead of setting your min for when you, instead of setting your minimum limit to 20 degrees outside air temperature, you increase that to 30. So it will hit your design condition sooner. So that's the advantage. Super easy to understand and to change. The downsides, though, you might have some tuning issues. Those reset limits, like I was using on the chilled water system, a 90-degree outside air upper limit and a 60-degree outside air lower limit. That's just my best guess. As an engineer, or if I were a building operator, they might have their own best guess, and it's probably going to need some adjusting to see what will work for your building. And you're usually leaving some energy savings on the table. Because if you set this up, and if all of your spaces are comfortable all the time, there's probably still room there to optimize. Because what's probably happening is you're still probably providing more heating or cooling than you really need under some of those operating conditions. Because these loads, they're not always 100% predictable. I know that's the assumption we've been running with on all of our bin calculations, but in actual practice, that's not always true. And there is a more efficient way to reset our temperatures rather than based on outside air temperature, and that's based on what's called a load-based temperature reset, also known as most open valve polling. The idea here is we're going to dynamically adjust the temperature based on what the active load actually is in whatever system we're looking at. So if we have a hot water system, we want to provide just hot enough water to serve the worst case active load out in the system. And that does not necessarily mean the worst case possible. That's how a design engineer thinks. I kept using that term, worst case. It's just what is the worst case right at this moment. Not necessarily worst case possible, just the worst case right now. And this does not look at outside air temperature at all. So if we had a hot water system, let's say we're sending out 180-degree water to a whole bunch of hot water coils out in the system. But if you look at your control system and you see, hey, none of my valves are more than 50% open, which means none of my spaces are calling for that much heat. They're all just cranking back a bit and they're saying, hey, we're good. We only need 40% of our flow or 50% or whatever. And what that means is the 180-degree water we're sending out, that's excessive. We don't need to send 180-degree water because all of our valves are just cranking back. And so we can then say, well, we can get away with colder water and still serve the load. So let's reduce our set point by 5 degrees, let's say. So we're going to go from 180 degrees down to 175 degree water. And then we wait. and we see what the valves do. What'll happen is the valves are going to open a little bit more because we're sending it water that's not as warm, so now they need a little bit more flow. So now you look at the valves, and now the most open valve is 65% open. And that's how we're deciding what the worst case is. What valve in the system is the most open? Because that's the one that's calling for the most heat. So all the valves opened a little bit more. Worst case now is 65%. We say, well, we can reduce that temperature even more. And you just keep doing that until your most open valve is at about 90%. Your most open valve is almost all the way open. So the idea here is we're constantly polling the valves to see where they're at. So the system's checking the valves, saying, how are you doing right now? Yep, you're good. Okay, you're at 60% open. Oh, you're at 90% open. Okay, you're exactly where I want you to be. I'm going to hold right here. I'm at the temperature I want to be at. But now, let's say the heating load starts to increase. So now the valves want more hot water. And now the control logic is looking for something else. Are any of my valves open more than 90%? Or are some of them open 100% and trying to get as much heat as possible? And if that's true, that tells us we need more capacity, i.e. warmer water. So now increase the set point and see how the valves respond. So it's kind of a back and forth. It's a constant polling of the valves, seeing where they're at right now, increasing set point, decreasing set point as needed to serve that worst case valve in the system. So the basis of savings here, you might have improved boiler efficiency if you're using condensing boilers, and additionally, you'll have that reduced distribution losses. So that's a lot of words. Let's try to visualize that. Here we have a basic hot water system with 3 control valves controlling flow to these hot water coils. We're sending 175-degree water. The control system looks at the valves, sees 65%, 70%, 75% open. It sees that and says, well, we can get away with colder water. So we reduce our set point to 173, which means all of these open a little bit more. There's still room there to optimize, reduce it again to 171. Now this third valve is over 90% open, so the system would probably stop right there. If you had a chilled water system, it would be the same logic. If none of your chilled water valves are more than 50% open, you probably don't need 45-degree water. We can make it warmer and save some chiller energy. So we raise the chilled water temperature, see what the valves do. Same exact idea as a hot water system, just on the chilled water side. So by doing that, we can improve our chiller efficiency and reduce our piping distribution losses. Supply air example can be achieved by looking at the damper position on your VAV boxes. So in this case, we're not looking at the control valves on a water system. We're looking at the VAV box damper positions on the air side. So we look at the VAV boxes. Nope, none of our VAVs are more than 90% open. That means our cooling load is low. So let's raise our supply air temperature set point. Check again a few minutes later to see where they adjusted to. And then going the other way, we have a box that is full open. It's saying I need as much cooling as I need. So let's lower our supply air set point. Just check again, just constant back and forth. To try to visualize that, we have a VAV box, well, a number of VAV boxes with an air handling unit. And recall, this is always providing cool air all the time. 55 is normally the design supply air. That's the coldest we would allow it to get. But we see none of our VAVs are that open. So let's increase our set point. These all open up a bit more, because if we're providing them warmer air, then the spaces will need more of that air to cool down the space. Still room to optimize here. So raise it again. Box is open again. Now we're at a good place to stop. So with a load-based temperature reset, having some kind of reset is really important. So imagine this scenario. We have a single duct VAV system, like we were just looking at, that's always providing cool air to these VAV reheat boxes. But let's say none of our zones are actively in cooling mode right now. Let's say we are moving 10,000 CFM of supply air with 1,000 CFM of outside air, and it's a really cold day outside, 0 degrees Fahrenheit, 70-degree return air temperature. So knowing those conditions, how much supply air, how much of that is outside air, what is our outside air temperature, and what's our return air temperature coming back into the unit, we can figure out the mixed air temperature. If we mix in 1,000 CFM of 0 degree air with 9,000 CFM of 70 degree air, we have a mixed air temperature of 63 degrees. But if we are supplying 55 degree air, if that is our active set point, so there's no reset being applied, that means we have to cool down the air to 55, only to heat it up when we get to the VAV boxes. So we're taking 63 degree air, cooling it down to 55, and then reheating it at the VAV boxes, because none of those spaces want cooling right now. So this would be an example of simultaneous heating and cooling, which the energy code takes great offense to. We're heating and cooling the air before it gets delivered to the space. So what if instead we reset that supply air to 65 degrees? Now we would only be heating up the air. We'd be taking 62 degree mixed air, heating up to 65, and then that goes to the VAV boxes, and then those finish out the reheat. So now we've taken away the simultaneous heating and cooling, where the systems would be fighting against each other, to now we are strictly heating the air from 62 to 65, and then whatever's needed at each space. Way more efficient way to do it. We take out the simultaneous heating and cooling, which, remember, that's one of the absolute worst things you can do from an energy use perspective. So really important to have some form of reset. I don't care if it's an outside air based reset where you're just interpolating based on some limits, or if you do it with a load based reset by looking at the boxes, just make sure you're doing something. And that brings us to pressure resets. We can use very similar logic on fans and pumps if we have a VFD that's controlling them to vary the fan or pump speed. If we had a load-based pressure reset, as a quick reminder, recall how VFDs are controlled. They vary their speed based on a pressure sensor that's downstream of the fan somewhere in the ductwork. Or if it's a pump, it'll be a pressure sensor in the piping, but it's looking at that pressure sensor and trying to maintain a constant pressure at that point, wherever that sensor is, by ramping the fan speed up and down. So as our VAV box is open, that reduces our duct pressure and tells the fan to speed up. Or if our VAV box is closed, that creates a pressure increase in the duct because now the air has nowhere to go, and that's going to speed the fan down. But what if all of our boxes are only 60% open? That means our fan's working harder than it needs to, and the boxes are just choking off that excess airflow and pressure. Just like thinking of a hot water or chilled water control valve that's just choking off water flow because it doesn't need all of that 180-degree water. So let's reset that pressure set point. Same exact concept as resetting temperature. And this same logic can be applied to a VFD-driven pump. Except instead of looking at VAV boxes, we're looking at control valve positions. So let's say we have a supply fan maintaining some static pressure set point. 1.5 inches water column is a pretty reasonable set point that we might see. So that's the pressure set point in the duct they're trying to maintain at all times by changing the fan speed. So we look at the boxes. If we're in a low cooling scenario, our most open damper is 65%. So our fan is working harder than it needs to, and our dampers are just closing off to just burn up that excess pressure. So the fan's running more than it needs to, which leads to a lot of wasted fan energy. So let's reduce our set point by 0.1 inches, see what happens. So now all the boxes will open up a little bit more. Our set point's now 1.4. So our damper, most open damper, 75%. We can decrease it again to 1.3 inches, and we just keep doing that until our worst case box is open more than 90%. And now we're good. Hold right there until possibly the inverse happens, or maybe we can keep decreasing later in the day. So if the reverse happens, cooling load increases, VAV boxes want more air, dampers start to open. So the fan is seeing that box full open, means we need more fan output. So let's increase the static pressure set point by 0.1 inches. Wait and see what happens. Keep doing this. So this will reduce your fan energy, and quite a bit actually. So the fan pressure reset, sometimes called duct static reset, that's a big energy savings opportunity. There's an ASHRAE study out there when this started becoming a big deal to reset the duct static pressure. There's an ASHRAE study that estimates 25 to 50% of your fan energy can be saved compared to not doing a pressure reset strategy. That's a pretty big number. I realize 25 to 50%, that's a pretty large range, but even 25%, that's a good amount of savings on the low end of that range. To visualize this, we have our fan VFD controlled off of our pressure differential transmitter, and that's set for 1.5 inches. All of our boxes are moderately open, so we decrease the set point, see how they open, still room to optimize, decrease it again, they open more, and that's a pressure reset strategy. And you might notice that or have thought about how in this VAV application, I talked about resetting the supply air temperature based on damper position in the box. Now we're also resetting this based on effectively the same thing. We are resetting the pressure set point, but that is correlated to a damper position. So we're using that damper position to effectively reset two different things in the air handler, the supply air temperature and the supply fan speed. And I realize I feel like I'm drilling this into your head pretty good. All of these reset strategies are fundamentally very similar in how they operate and what the control logic is doing, but it's a very powerful thing that can be used in a lot of different applications on the water side and the air side. So I think it's pretty important to understand how this works. So in summary, if we have a load-based reset, the advantages of a load-based reset is we're better able to optimize our system based on actual varying load conditions. And this is going to give better energy savings compared to an outside air temperature reset that just looks at outside air temperature and then resets your, uh, well, whatever you're trying to reset based on the outside air temperature. The downsides, though, this is more difficult to program and to make adjustments. As compared to an outside air temperature reset strategy that's very simple, very easy to understand, and easy to adjust, this takes a lot more control logic, brain power to make happen. If you can imagine a building that has 300 VAV boxes, now your control system has to be smart enough and powerful enough to look at all 300 of those boxes and see what's going on and see what's my active damper position at every one of those boxes, and then adjusting the program to serve the worst case condition. You can also have a rogue damper or a rogue control valve that is always near that max position. And the issue there is that will drive the entire system. If you have a hot water system, let's say every control valve right now is only 30% open, but then for some reason you have this one control valve that is 100% open. Now that one control valve could end up driving this entire strategy and forcing the system to provide 180-degree water no matter what. So that would be a rogue valve. Or you could have the same thing on a VAV box. That would be a rogue damper. And this is likely caused by bad design or bad sizing of that valve or that damper, or maybe they might have changed how that space was used without redesigning the system. One example might be, let's say you have a chilled water system and there's a space that used to be an office, but they have decided to change it and load it up with a bunch of server equipment. And so now that little tiny office needs a ton of cooling because of all that server equipment you just shoved in this tiny closet, and the chilled water valve serving that room is now too small. And so it's always going to be maxed out, trying to get as much cooling as it can. So that rogue damper or that rogue valve can totally invalidate a load-based reset strategy. You can spend all this time programming this in and then have the whole thing derailed by one damper or valve in the system. And if the control system is smart enough, what you should actually have is some logic in there that can tell you when you have a rogue damper or a rogue valve. You should have some logic in there that's checking to see, hey, this one damper has been driving the reset strategy 100% of the time. Maybe you should go look at that. So the way you'd identify that is if you have one damper or one valve that's always pretty much maxed out, but everything else on the system is below 50%. These are all approximate numbers, but the idea is you have this one valve or damper that is totally on the extreme as compared to everything else. And that would tell you that's probably a rogue piece of equipment, and you should look into that and get it fixed. All right, that is all I got for today for this class. Any questions on that?